Hey guys, today we will learn about also inductor part. But what I mean is we wanna know why the fault current, yeah, for example, short current, the waveform is kind of asymmetric. So today we will learn about why it, why it become like a asymmetric waveform. Okay, so this is the result is because of inductor, you know. So I explain about more. Let's see. Uh, yeah, let's move on. So what I meant is here, look at that. Asymmetry, the blue wave form. Why it happened? The red one is symmetrical, right? But blue is a fault current. Why it happened like asymmetrical? Why it happened? And what does it mean DC opposite? And why it happened like this? So I explain, okay? Let's move on. Yeah. So look at the guys. We know about this, right? It's a inductor's equation. We have to memorize. So I wrote down one more with T, L, T, D, I. So time goes by. If the I or flux is changed, the V is induced, right? So this is a time function, right? Time goes by. Well, I want to see it in the pager, right? So V pager. And you guys remember dt, I will say j omega, which means, 90, j means 90 degrees lead. You know what I mean? So that's why it becomes the V is a lead. You know what I mean? I is lag in the inductor, right? So V pager L J omega I, right? But impedance is I V L J omega, right? Omega is angular velocity, right? So I will change it to L J 2 pi f, right? Yeah, this one. And as you know, impedance is R plus JX. But in the inductor, there's only imaginary number, right? So JX is here, look at that. Yeah, JX is equal to this. Yeah, and this is a frequency, right? Yeah, yeah, so yeah, what I wanted to say is, sorry about it. So look at that. I wanted to show you guys getting one more time how do we get this equation. So you just remember this equation. It's fine. You don't need to remember this part. Okay. So what I wanna say is, first of all, inductor, the coil is inertia. Inertia's component, right? So for example, uh, look at that. For example, this is a car. If we fast speed, if we runs fast speed, so if we wanna stop it, the inertia is really strong, right? But if it's slow speed and stop it, inertia is really low. You know what I mean? So same concept. So what I mean is, if the current change is really sharp, you know what I mean? Sudden change is really sharp, really big, the magnitude. It means more inertias, make it. This is the concept of inductor, right? So I said before in the DC circuit, look at that. This is L. So what I mean is JX, right, in the circuit. And this is load. And so if I see it, the graph, here's time, here's current, here's, for example, 10 ampere. So like this, right, the graph is. So this part is only changed, right? And this is a steady state. You guys remember, right? This is a transient, state. It's changing, you know what I mean? So also, what happened in the AC? Let's see, the AC. First of all, I will draw like simply the power, system. Like this is a generator. This is R, and this is JX, and this is load. For example, this is the simple power system, right? JX, and load is gonna be like parallel. If we add more load. By the way, now I will say in one load, okay? So what happened if the short happened, short happened. So here's the short current, IS. Short current is happened this side, right? So what I wanna say is if the short current is a short current is a fault current, right? But in RL circuit, even we switch it on and off, it's happened the same, situation. The asymmetrical waveforms happened because of the inductor. You know what I mean? So it's the same concept in the fault current happened, or it's whenever we switch on and off, it happened. So I'll explain more about it. So look at the guys. This is graph. So first of all, I will do a voltage here. This is voltage, okay? This is V. And as you know, inductor is look at that. Inductor is 90 degrees, lag, right? So if we look at that now, current is I is 0 ampere. Yeah, I is 0 ampere here till here. This is switch on and off. Okay, this is I will say switch. So now the V is 0 degree here. V, the black line. Okay, V is 0 degree. And if we switch on, the current is happened like this. I will do purple. So 90 degrees later, the lag 90. Current is happened like this, right? So look at that. Before here, if we switch on the point here, this specific point, right? So I is 90 degrees lag, right? But look at that. For example, here is a minus 10 ampere. Here is minus, and here's a 10 ampere plus. But look at that. Because of you guys know, I said the current is, the inductors cannot, change right away. It needs some time, right? So look at that. Because of inertia, minus 10 amperes inertia. So it happened here. I will do it this color, green. Yeah. So the inertia made it this 10 ampere. You know what I mean? So that's why it started from to here. But look at that. But I wanna say is this period. I will say this line is DC opposite because of inertia. It happened. But I will say you guys remember may tau Rx this. If the R is small or R is I mean, yeah. No, sorry. If the L is big or small, also same. R is register is same. The tau's time is depending on these two values. You know what I mean? So if it's the tau's big number, which means it disappeared, this opposite disappeared, more slowly. But this is exponential functions. You know what I mean? Exponential functions here, like this, smoothly disappeared while smoothly increasing. We will say this is in math. In math, we will say exponential. I don't know, exponential function. We will say so because of inductor, it disappeared exponential function. You know what I mean? Like this smoothly. So that's why we say yeah, this is a DC opposite. And look at that. What happened? Which color? Red color. So look at that. Now, because of this DC opposite, so that's why the current, but look at that. The port current is started not from here, As you guys may study a little bit about the port current. Port current is started from 0 ampere because of inertia, 10 ampere, 10 ampere. And then the current follows from this line, DC opposite line. So that's why start from here like this. You know what I mean? So like this. And later it gotta be like a symmetrical. Now it's asymmetrical, right? This part and this part is a different, right? Upside and downside. This is a different magnitude, and also looks like the waveform, right? That's why we say asymmetrical. And it happened when it's the current is port current happen, right? For example, short current, or even because of we just switch on and off because of inductor, it happened. So yeah, that's why it happened. It's naturally, okay? Yeah. Yeah, let's move on. I'll show you guys pictures. Yeah, look at that. What I said is this is DC opposite, right? It's a exponentially, exponential function, but disappeared, slowly because of inductor, right? And then because of the inertia, it happened, right? DC opposite. And this line is now standard for the port current. You know what I mean? The blue line. And then time goes by, this DC opposite, I said inertia is, not constant power. It disappeared, right? That's why time goes by, it gotta be like asymmetrical. It disappeared. Yeah, that's why this is what I explained. And let's move on, guys. So since we use a 3-page system, right? So what I mean is, okay, let's move on. For example, guys, look at that. So we were like start the V is before I draw the V is 0 degree, right? But I is 90 degrees lag, right? But what if like if we do 90 degrees here? So look at that. For example, this is V. So this is switch on, right? Switch on, this yellow line switching. And as you know, I is, 90 degrees later it happened, right? So look at that. If the I, V is now, we switch on here, right? I is happened from the 90 degrees later here part, right? But this time, look at that. If I is happened like this, what happened this part? Look at that. There's no inertia. Now 0 ampere, right? That's why. It's some, it happened like 0 amperes. You know what I mean? So there's which means no inertia. You know what I mean? No inertia happened. But sadly, look at that, guys. Since we use a 3-pager system, so those switches on and off, simultaneously, same time. But what I wanted to say is even though we do a 90 degrees, when the voltage is 90 degrees, and I is after then start from the 0 ampere, the inertia is 0, right? But even if there's no, asymmetrical waveforms happened, symmetrical waveforms happened, but because of we use a 3-page system, so after 1 to 0 degree, second, current is also happened like this, and then the 1 to 0 degree and also happened. So that's why it has to be like a asymmetrical. Let's see here. So look at that. Oh yeah. So yeah, I explained that. And then look at that. We have a 3-page system, right? So look at that. This A line. So A waveform. This is for example, minus 10 ampere here, right? And because of inertia, DC opposite here, plus 10 ampere happened. So that's why the standard line is here. The red line is so this part like this. And what happened? The second B line, look at it here. B line is plus. So it gotta be the DC opposite is minus part here. So look at it here. But I said that this appeared like a exponential function, right? Like a slowly, not that change it like suddenly not changed. It needed some time, right? And what about C here? C is more upper side than B, right? So that's why the inertia is more lower this side C. So C is happened here. That's why this 3-phase waveforms, asymmetrical waveforms happened in 3-phase. But this is kind of not easy to understand, right? If we just see this waveform. So that's why I explained just one waveform. You know what I mean? So this is because of inductor, it happened. Yeah, today lecture is done, guys.